Have any questions on what we covered last lecture? All right. So what we're going to cover today is we're going to start going into this concept of performance. So recall that the basic philosophy of MIPS is the high performance execution of compiled code. So before we get to the idea of what compiled code is and how you actually translate it using the compiler to get from the machine code to from the assembly code to the machine code and then executing in the 5-stage data path, you need to be able to understand what performance is. So we're going to be going over the details of what performance actually is, what execution time is, what throughput is, and how you actually can start to design a computing and advanced digital system to improve computing performance. So the first three concepts, they're all related to each other in TGO 1.11, are execution time, throughput, and performance. So execution time is the total time required for a computer to complete a task. Now that seems relatively intuitive, but when you're working on these problems, what you really want to understand are the units. Specifically, seconds or seconds per instruction. So an instruction is each computing instruction that is being completed by the data path. So when you're working out these problems, a lot of times what I'll often say as we're working through them is the units will set you free. Meaning that you get on the exam, you see this big word problem, you start to panic, and completely, I completely forgot how to do this. What you want to do in that situation is just start writing out the variables that I put in the problem and start writing out the units. And you'll start seeing like, oh, if I multiply this and multiply this together, they'll start canceling out, and eventually that item that I have to find. So in this case, if I say find the execution time, and I give you a number of instructions, and I give you some sort of time, as a basic as we'll go over here in example 1.1, then suddenly, oh, hey, I know that. So you just put them together, divide them, and suddenly you've derived the equation by yourself, right? So the second one here is throughput, the number of tasks completed per unit time. So throughput, very simple. Instructions per second. So basically, throughput is the same thing as 1 over the execution time, right? Because you can see that these are the inverse of each other. So execution time is how long it takes. Throughput is the number of instructions we've completed over that time. And then performance is actually the same thing as throughput. These are synonyms. We say computing performance. What I actually mean is I want the computer or the advanced digital system to perform as many instructions in a given time as possible. So high performance execution of compiled code, what that means is I compile the code, I come up with a number of machine instructions, and I want them done as fast as humanly possible. Does that make sense, kind of seeing what these terms are? So when you get into these types of questions and people are throwing out terms like throughput and performance and execution time, when I was first TAing this course way back years ago, oftentimes students got really confused by these terms. So that's kind of where I got the idea of how maybe I should do topical guided sections, because you go through, students write out the terms, then you start having the questions relate to the terms, and these are the terms that are also used in industry. So you go there and you sound like you know what you're talking about when you get an interview. So example 1.1 here, down kind of the bottom. If computer A, this is a very simple example of how performance and execution relate to each other. If computer A runs a program in 10 seconds, and computer B runs the same program in 15 seconds, state the improvement in performance of A over B. So performance, so we want some sort of ratio that's greater than 1, because here we already know that there's an improvement in performance. So that makes it a simple problem. If you have a problem that we come around with later, and I say compare the performance, and you do this, and it comes out to less than 1, what does that mean? the one in the denominator is the one that runs faster. Okay? So in this case, we have performance A over performance B. In fact, I can zoom in here for those of you in the back. So performance A over performance B, this is equivalent to, so now I'm coming up with a ratio. So we also know, based on the previous topical guide objective, that the performance is 1 over the execution time. So this just basically means that it's 1 over execution time of A equals 1 over execution time of B, which we simplify to execution time of B over the execution time of A. So we know in the problem that execution time of B is 15 seconds, execution time of A is 10 seconds. That means we have an improvement of 1.5. And so all the homework assignments that are due are all the topical guide objectives and example questions. So if you go on Blackboard, oh yeah, one thing I got a lot of emails about, you don't necessarily have to write each topical guide objective question and then the solution, because you have them available on Blackboard for you. So you can have the guide that you refer to on your notes. So that should save you time on when you're writing up your submissions. Okay, does anybody have any questions on how this question was worked out here? It's relatively simple, but the reason I'm including it is so that way you get an understanding of the terminology. Yes?
This question isn't the same that was on the...
Hey, don't worry about that. All right, any other questions? All right, yes.
The example questions that we have on Blackboard.
All right, don't worry about those. The example questions, I'll make sure they're updated. Fine.
That's not what I was going to ask.
Okay.
Are they going to be? They're strictly for us to study. Like we're not going to have to turn them in for anything. Like
no, you do.
They are.
Yes, they are. I would expect all TGOs and example questions to be turned in. Any other concept questions? Yes.
Oh, I'm just going to ask, is this the exact example question that's going to
be? Yeah, you're going to be, when you turn in your homework assignment, I expect this solution to be submitted. Yeah, any other concept questions? Okay, good. So high-performance computing is widely recognized and regarded as an essential tool for enabling science as an indispensable, integral part of virtually all SC scientific research endeavors. That's Dr. James Decker, the director of the Office of Science in the Department of Energy. Well, he used to be during the Obama administration. All right, so topical guide objective 1.12, this is where the terminology kind of gets a little more complicated. So clock cycle time is the time for one cycle generated by the processor. So what we mean by that is if you've ever seen a waveform, digital waveform, since you have advanced digital systems, or if it's an analog, you're familiar. So with a digital system, we have the beginning of one to this is one clock cycle. Right here, you see how it goes through the entire cycle and it comes back to where it was. So that the length of one clock cycle, actually, the length of one clock cycle. So rise time to rise time, or fall time to fall time. This amount of time is defined as the clock cycle time. And that's the time for one cycle generated by the processor. The clock rate is the number of cycles per unit time. So if I have 10 seconds here, and I'm coming up with a number of different cycles here. So then we start here 1, 2, so that's 1, 2, 3, 4, 5, 6, 7, right? So 7, we just say this is 10 nanoseconds, then what this becomes is, number of cycles per unit time. So it's 7 over 10 nanoseconds. So the units is cycles per nanosecond, and that's why I've included cycles per second there. So see how I was able to derive the value? So because the clock rate is equal to the number of cycles per second. And then it becomes intuitive that the clock cycle time is 1 over the clock rate if you have a unified cycle. And then the cycles per instruction is CPI. So we have the cycles per unit time, but when we have, that's a terrible drawing, but bear with me. So we have instruction number 1 and instruction number 2. We'll be doing derivations over how many cycles it takes to perform a particular program. So that's going to be later in the lecture today, average cycles per instruction. And so that's going to be a problem we'll work through. So we have cycles per unit time, and then let's say you have, like we had 7. You do not need to scan in. Sorry, you missed me going over that earlier. So if you have that, and then in that time you can actually do 3 instructions in that time. Well, then it becomes, if you're doing 3 instructions in those 7 cycles, then that cuts down on your CPI because you can get 3 instructions, that's 7 over 3 divided by 10 to the negative 9. Does that make sense? We'll go over a lot more example problems, so we'll make this concept more clear. And then last, CPU execution time. These are all of the possible conversions that you will use. I found if you work through these before hitting a big example problem like example 1.2, you can actually see how all of the units cancel out. So CPU execution time, so you have CPU clock cycles times clock cycle time. So that's cycles times seconds per cycle. So you see how those cancel out and become a time? Same thing, CPU cycles divided by clock rate. So cycles over cycles per second becomes the same thing as cycles times seconds per cycle, and those cancel out. See how that works? Instructions times CPI, so that's cycles per instruction. So the instructions cancel out. Then cycle time is cycles, seconds over cycle, and this is cycles over instructions times instructions, right? So if you have a problem where you have a number of instructions, and then you get some sort of CPI, and then you get some sort of cycle time or clock rate. So here it's divided. You can see how these just cancel out, and you get execution time. But before I move on to the example question, does anybody have any questions about how those relate in terms of units and all those different terms? All right, so example 1.2. And a program runs in 10 seconds on computer A, which has a 2 gigahertz clock. So before we go on, what does gigahertz mean?
1,000 hertz.
Okay, so let me be more clear. What's the 10 to the what? 10 to the 9. That's so 2 times 10 to the 9 hertz, which is also what you said. But that's, and you see as we get down to the actual problem, that's how it's going to manifest itself, which has a 2 gigahertz clock. Computer B runs the same program in 6 seconds, but requires 1.2 times as many clock cycles as computer A, what is the clock rate for computer B? And oftentimes you're not going to know the clock rate. So this is a good way you can run a program on computer A, run a program on computer B. You're actually able to analyze how many cycles it took, and from there you're actually able to generate, you can calculate the clock rate. So sometimes the operating system can obfuscate that. So the CPU time of A. So what do we know? We know from the topical guide objective of these equations here. So we want to be able to get clock cycle. So the number of clock cycles is equal to the CPU time times the clock rate. We know that computer A runs the program in 10 seconds. And we also know that the clock rate is 2 gigahertz. So what we want to do is we have seconds, and then we have cycles per, we have 10 seconds and then cycles per second, right? So we're trying to calculate clock cycles. We're able to get 10 seconds times 2 times 10 to the 9 clock cycles. So that comes out to 20 times 10 to the 9. And the reason we want to know that is because we know that the number of cycles it took, the computer B requires 1.2 times as many. So the first thing we want to do is we want to find that connection between computer A and computer B. So first step, we know the clock rate, we know the amount of time it took. So we're able to get the number of cycles for A. And then from there, we can compare that to B, which is 1.2 times the number of cycles as computer A. So in this step, and let me zoom in so those of you in the back can see. So now we've derived the number of cycles. So then the next thing we do is 1.2 times the number of cycles of A, which is 20 times 10 to the 9. So that becomes 1.2 times 20 times 10 to the 9 cycles, which becomes 24 times 10 to the 9 cycles. And then we want to find out the clock rate for computer B. So we know from the topical guide objective, their CPU time is equal to the number of clock cycles divided by the clock rate. Here's what we want to find. The ultimate thing we want to find in the problem is clock rate. So what we're doing here is we rearrange our equation. We bring clock rate over here and then put CPU time of B down here. So now we know the number of clock cycles required to execute time B. To execute the program on computer B. We know the amount of time it takes. So we've derived that it's 24 times 10 to the 9 cycles. We know from the problem that it's 6 seconds. So it's going to be 24 times 10 to the 9 divided by 6, which is going to be 4 times 10 to the 9 cycles, which just becomes 4 gigahertz. Does that make sense? So one thing I should note, when I give exams, the problems will come out with numbers that are relatively clean like this. If you start getting 3.18723, you have the wrong answer. I deliberately arranged the question so that way you do not require the use of a calculator. So the first step, we go through this problem, is we know that so what let me give you some advice here on the exam. If you were to do this, you want to write given. So we know that CPU time of A equals 10 seconds. We knew the clock rate equals 2 gigahertz. We knew CPU time of B is equal to 6 seconds. And we knew clock rate of B is equal to 1.2 times clock rate of A. So from there, you can actually derive these equations. And then you find CPU time of B. So whenever I took exams back in the day, that's how I would do it. Just lay out the given and find, and you write them in the units, and then go, oh, hey, this is what will come out. Does this make sense? Is there anything about this that doesn't make sense to anybody? All right, so let's go on to example 1.3. So suppose we have two implementations of the same instruction set architecture. So I'm going to underline key details that you're going to want to look through as you're going through the problem. I'm going to explain to you very clearly what I mean by them, so that way when you get to a quiz or an exam, there's no ambiguity. Computer A has a clock cycle time of 250 picoseconds. Does anybody, so we know that giga is 10 to the 9, right? What's pico? 10 to the minus 9, correct. And a CPI of 2.0 for some program. So computer B has a clock cycle time of 50 picoseconds and a CPI of 1.0.